that.
So during last office hours, I was suggested that we should check attendance for this class. You think it's a good idea to start today?
Yes.
Okay. Those who are attendant, please raise your hands. Okay, you're out.
Okay. So this class today is kind of somewhat independent of everything else that you have heard or are going to hear. We did choose it because tomorrow is Thanksgiving, so we're not sure how many people could make it. I'm happy you did. But the basic question I want to try to address is this one. Why are the networks that people use today deep? Why are not shallow? What is special about depth? Why do they work and when? And with shallow and deep, I mean things like this. Network that typically have one hidden layer, I'll call shallow. And networks with more than one hidden layer, I'll call deep. Even in the shallow one, you may have one layer of parameters only. We'll see a couple of examples, or two layers. We'll see some examples. Now, there is some history behind it, which is kind of interesting. In the 80s, there were, I remember it well, I'm old. I remember it well, so there was a time in which neural networks, meaning shallow neural networks, were very fashionable at NIPS and other conferences. And then now in 2018, the shallow neural networks have just disappeared. And if you look back at that piece of history, one reason why shallow neural networks, people focused on shallow neural networks at the time and not on deep networks, was a result in approximation theory, very much in the spirit of today, so we'll speak about it today. And this was the fact that it was known, several people proved that shallow neural network, meaning one layer, are enough to approximate any continuous functions arbitrarily well on a compact domain. Something like Weierstrass theorem. How many people know Weierstrass theorem?
Yes.
Should be everybody, Polynomials can approximate any continuous function arbitrarily well on a compact domain.
Would that actually be problematic?
Sorry?
Hypothesis class would be too rich.
I'm sorry?
I'm just wondering, wouldn't that lead to estimation error? Weren't people worried about very rich hypothesis class?
Well, but okay, we'll come back to that. But at the time, one of the reactions of people was saying, okay, shallow networks can do this. We don't need deep networks for it. So let's focus on shallow. And this combined with the fact that deep networks were too expensive at the time for the computers of the time, made the situation in which deep networks were kind of abandoned, and the focus was on shallow networks, and in fact also on supervector machines that are another case of shallow networks. Let me try to get back to logging in. Okay. So now in the case of what I want to tell you today is really about approximation theory. And from this point of view, it's just one point of view, why depth, so more than one shallow layers, may be better. And so we have, let me just go. So if we have shallow network, this is one example, hidden layer. You have a d-dimensional input. So this is in RD. And you may have a situation like this one, which would be typical for kernel machines, in which your Y is a linear combination. In this case would be this 2, 1i, I to R of k x xi, where k is a kernel, could be just a dot product or a Gaussian kernel. And each of the R units will contain one of the examples in the training set. Okay, so there is no weights in the first, in the very first, going from the input to the first layer, and then these are the weights of the linear combination. And as we have seen in previous classes, this comes from this type of minimization problem in which you are looking for a function in a reproducing kernel Hilbert space, and you're minimizing some cost function, in this case the square error, and then you have a norm defined in K. Okay? So when you look at the solution of a minimization of this type, this is the typical solution you find. And this corresponds to one hidden layer network like the one above with one set of weights. Okay, so now another example is the neural networks of the 80s, in which now you have units which are, at the time they were sigmoids, so univariate nonlinearity shaped like a sigmoid. These days are an RLU, so this would be typically these days you're using a nonlinearity, which is defined as the max between 0 and a variable, and so it will have a shape like this. So 0 and then linear. And the network in this case will have two sets of weights. So you have essentially a dot product. I call each of the I are the hidden units. And then it's a dot product for the vector of weights associated with each I with the input. And then it's a linear combination of the output of the sigmoid with the weights of the second layer. And the output is linear. I don't have any nonlinearity at the top. That's the kind of standard networks that were used in the 80s and also today, if you have just one hidden layer. Usually you would be using the typical form would be something like a sigmoid of, this is now a vector dot product with x plus a shifts. But for simplicity, I get rid of the shift in what follows, and assume that one of the components of the input, say xd, is actually 1 constant. And so this weight will become equivalent to the BI, okay? Okay, so the deep networks would be then some iteration of this architecture. So you have the input, you have a set of weights, you have units that summates all the weights, the inputs with their weights, and then apply to it this univariate RLU, and then the process repeats. Yeah. Sorry? I'm sorry?
Even if the input has a 1 appended, the intermediates won't have a 1 appended.
No.
Okay. So this is no bias term?
Sorry?
I'm just worrying about the bias terms for the intermediate layers.
Yeah, they don't have the 1.
Okay.
This will be okay. I mean, you can have it or not have it. I'm not having it because it does not change anything in what I'm going to say about approximation, and it simplifies the notation. Okay, so this, you can write it with some abuse of notation as something like a matrix for layer L, and this will multiply some other matrix, JK, this will be layer L minus 1, and this will be a sigma, again, of W, say KP, KPX. So for instance, you have dot products between vectors indexed by k with the inputs, one vector for each one of the hidden units in the first layer, and then each one will be multiplied with the matrix of weight at the next stage. When I write this, I'm using what is called the Einstein convention, which means that I'm summating over repeated indices. Okay, for instance, here I will have a W, some LP, sorry, K, and that will summate over K there. Is that clear? No? It's like, let me see, maybe I had it here before. Yeah, it's like here. Here is not, is explicit. I summate over I here, but in the notation I just wrote, I don't write the explicit summation. People. Okay. Okay, so we have all these networks, and I want to think about this in terms of function approximation. How good are they in representing functions or approximating functions? And so the first question is, are deep networks better than shallow networks for approximation? And you know, the answer in the 80s was already so what we're going to do is to see a proof of the above, and also because this will give us a way to, for a new result that shows why depth can be better. By the way, can you read my writing? Kind of. Okay. Okay, so first of all, let me introduce a couple of very simple ideas about functional approximation. So in functional approximation, you have typically a function, a space of function that you want to approximate, say the space of continuous functions, for instance, and another space, which is the space of the polynomials or the parametrized schemes, or in our case, the networks you want to use to approximate the function, okay? So you have these two things. One is your target, the other one is what you want to use to approximate the target. And so, for instance, a typical example is that I have a function, and so this is not a network. I use this graphical notation. It's a graph. It's just to note a function, okay? But this one, I use this notation to say it's a network with one hidden layer. Now, I'm adding that I want to consider function f such that they are in continuous in function with d inputs. Continuous means, of course, that I can, for any epsilon, I can find a delta such that this is less than epsilon, okay? And here I have to say, for instance, that my networks will be some g in a space of, let's call it the span of sigma w I j x j, say. So this means that I look for networks that are linear combination of RLUs, and I have n hidden units. Now, so this is function and approximator. The next very simple notion is the one of density. So I say that if I have a function, say any function that is in continuous, the variables, and now I consider a compact set K in RD. Now, for any G in Vn, if for any G in Vn, no, for any F, there is a G such that sup of f of x minus g of x is less than epsilon. So this means that in the set of my networks, I can find at least one which is approximate within epsilon over the whole domain, any function in that space. Then I say that V is dense in K. Have you seen the notion of density before? Okay. Now, still another concept is the idea of degree of approximation. And that's the one we need to extend all the results of the 80s. And degree of approximation is a simple idea. You are saying how many units do I need to achieve that approximation? How complex is, how high is the degree I need? The question is how large is because it turns out that in the results of the 80s, people took a result like this to say, okay, shallow network can do pretty good job, but they did not really worry about how large this is. And it turns out that n can be very large. In fact, we can have a theorem here, and now I'm putting some more structure on the function I want to approximate. They're continuous, but they're also in a Sobolev space, so they have some smoothness. So the Sobolev space, WDM, this is, my notation has functions with function of d variables with a smoothness m, in the sense that this norm, which is defined in terms of the derivative of f with respect to all the variables up to degree k, that is bounded. So this gives a certain smoothness to this f. Okay. So if I assume this, there is a theorem, and that's a classical one, which we are going to prove, is that using this kind of one-layer networks with sigmoids or RLUs, I can get an approximation within epsilon of this function in the Sobolev space, and the number of units I need are 1 over epsilon to d divided by m. So suppose, for instance, that I have no smoothness, so m is equal 1. You know. Then what this says is that if I want an error, a maximum error of, say, 10%, epsilon is 0.1, and then the number of units I need is 10 to the d. Smoothness helps to reduce this number. But say, take the simple case, I really know only it's continuous, then it's 10 to the d. Okay? And you can see immediately that, you know, if you have 2 dimension, okay, it's 100 units. If I have an image of 100 pixel, which is not very much, is 10 to the 100. It starts to be a large number. Okay, this in fact is called the curse of dimensionality. And this is a term that was invented by Bellman, who developed quite a let's see, quite a bit of optimization control in the 50s, 60s, 70s. The curse of dimensionality is a recurring theme in many areas of computer science and science. It has been taken to mean that you cannot do optimization by random search because you have to explore too many possibilities. It makes multidimensional integration very difficult. And in function approximation, it has similar implications. In high dimensions, you have this exponential dependence on dimensionality. For instance, you have a function, a Lipschitz function with Lipschitz constant epsilon. For function approximation, you will need in the order of epsilon to the d evaluations. And so, we can have some examples. For it's a typical example, and this we'll come back to this later, is a polynomial, say a polynomial in d variables, let me denote it this way, of degree k. Okay, this has, any of you knows how many monomials? Sorry?
D plus k choose k.
Yeah, it's d plus k over k. And this is d plus k factorial dk. And this is very roughly, you can say it's k to the d, or depending, is d to the k. Something in that order. So as soon as k and d become large, these numbers are large. Another way to look at it, so that's one example. Another way, and you get the same, interestingly, the same kind of number. So this is the type of things if you are an old-fashioned mathematician, you're using polynomial. But if you are a computer scientist, you may think of a function, say, of 10 variables as a table. And so this will correspond to a 10-dimensional table. Now, for each one of your dimensions, for each one of the x. Now, suppose I have only, 10 values for each one of the x. So 10 partitions, not very many. It's like 3 bits, 4 bits, between 3 and 4 bits. And then this 10-dimensional table will have 10 to the 10 entries. Okay, you see how quickly this increases. And as I said, if instead of x10 you have x100, then your entries for 10 partitions only per xi, the entries are 10 to the 100. I forgot how many protons in the universe, but I think it's less than 10 to the 100. I may be wrong.
It's 10 to the 80.
Sorry?
Well, 10 to the 80.
Yeah, exactly. So it's less than 10 to the 100. That's the number of protons in the universe. Thank you. Okay. Now, there are, some blessings. So there is the curse of dimensionality, and there is the blessing of smoothness. And this is because this stuff goes as d over m, where m is essentially the number of derivatives. So if you have a very smooth function, you can make your dimensionality effectively smaller. And by the way, all of this is consistent with, how many of you know Shannon theorem, Shannon sampling theorem? No, not many, but again, the Shannon sampling theorem is a similar structure. You need a certain number of samples per cycles. Suppose you have a signal with a maximum frequency f. You you need 2 samples per cycle, so the higher the frequency, the higher the number of samples. This number of samples is exponential in the dimensionality, if you have a 2 3-dimensional signals. But if your signal is smoother, so your higher frequencies goes down, you can cut your minimum sampling interval. Right? So it's exactly the same story. Okay. So let's first go through the proof of this statement. A network, how many units you need for a shallow network, 1 layer, for approximating a function. And then we'll see how this gives us an idea to find another way, another blessing that I will call blessing of compositionality. That's a new thing. Okay. So let me first so we want to prove that networks with sigmoids, and we'll see in the proof that the type of nonlinearity, whether it's RLU, sigmoid, does not matter. Cannot be a polynomial, otherwise everything is fine. And the logic of the proof is the following. I'll first prove that networks of that type, shallow network with sigmoids, can approximate arbitrarily, well, with, I'll give you numbers, with a certain number of units, univariate polynomials. Polynomial in one variable. And then we can show that we can write any polynomial of many variables in terms of combinations of univariate polynomials, where the argument is a dot product of this type. And so the combination of 1 and 2 will tell us that networks with sigmoids, 1 layer, can approximate multivariate polynomials. The first step is just using known results that multivariate polynomials can approximate at a certain rate so with a certain number of units in our case, functions in a Sobolev space. So these proofs will prove not only the density, which is the result in the 80s, but also give us degree of approximation. Is that clear? So the first step is to prove this, that assuming that sigma is not a polynomial, and I'm assuming here there is a proof also in excluding this, but I'm assuming that the sigma is infinitely smooth. Okay, that's not true for RLUs, but you can assume that you are making the kink smooth, locally very smooth. By the way, this is on the side, but we have just done some experiments in which we replaced every RLU in a network used for classifying CIFAR or ImageNet. We have replaced it with a univariate polynomial. I think of degree 9, and the behavior is exactly the same. Okay, so let's assume this. And so the statement is that essentially combinations, the output of a network, which is combination of sigmoids, and there are limits, that's the closure, but we'll see what happens, represents exactly the space of polynomial in one variable. So the argument is pretty simple. It goes like this. So this would be the proof. Consider this. Consider a combination of two units. So one will be, let me write this way. One is ax plus b, so it has an input x, coefficient a, x, we are in one variable, and have a nearby one, which is a slightly increased coefficient, and then coefficients that do this, and then I take the limit for h going to 0 of this linear combination. Okay. Now, what is this? Remember the definition of the derivative? This is the derivative with respect to A of sigma AX plus B. Right? Do you agree?
Is A constant here?
Sorry?
Is A constant?
Sorry, I had one parenthesis missing here. Maybe this is. Sorry. I think otherwise it was too simple. Is that okay now? You are right. Okay, so, and now if I evaluate this at a equals 0, I have essentially x derivative so by a linear combination and the limit of this, I can get the first term of a polynomial x. This is with 2 units.
Where did you get the a equal to 0?
Sorry?
Where did you get the a equals to 0?
It's just that I can evaluate it, for instance, at a equals 0. I take a derivative, right? I have, if you want to write this, I can do, let me use the, by the way, this is an experiment in using this tablet, so this would be without, let me see, without this would be sigma prime ax plus b, okay? But then I can say I evaluated this at a equals 0, and then, for instance, with the RLU, if b is positive, I know that sigma, the derivative is positive. And yeah.
So we also use the fact that sigma prime of b is non-zero, right?
Yeah, that's what
I
I just said. Yeah.
Okay, but
Yeah.
I'm saying like this is generalized to the non-polynomial constraint.
Sorry.
This is generalized to the non-polynomial hypothesis for higher orders. Is that where it comes from?
Yeah, yeah, it does. It's for instance, for the RLU, the derivative, of course, is not 0 when the argument is larger than 0, right? Because you have a constant. So it's enough to ensure that this would be positive. If I combine 3 units, what can I do? Sorry? Second derivative, yes, exactly. It's like, you know, plus 1 minus 1 plus 1, right?
Minus 2, right?
Huh?
Plus 1 minus 2 plus 1.
Yeah. Yes. And then here I'll get x squared
With the
by
second
doing the
derivative,
same
that's
thing.
where you get the non-polynomial.
Yes. And so I can get all, you know, all the monomial of a univariate polynomial just by taking linear combination of units. And the degree, you can see I get degree 1 with 2 units, I get degree 2 with 3 units, I get degree 4, 2, 3 units, degree 3, I need 4 units. So 1 unit more than the degree. Yeah.
So here we're organizing sort of a filtered union of complexity classes based on how many units we have, right? But it seems like we're using some like ill-conditionedness of it such that we change it slightly, we get this difference. And I guess, are there analyses where we quantize the weights or something so we can't have infinitesimally different weights? Because it seems like
In this analysis, you don't quantize weights. There is a parallel analysis you can do in the computational science framework in which you don't use actually polynomial, you get the same type of results. But let's follow this is the classical one, back to the 80s. There is a good review, I don't know whether it's in our, by Pincus, which is an approximation guy. The results are by a number of other people, but that's a good review. I can put it on our okay. So by the way, this means that not only that our combination of RLUs or sigmoidal units can approximate, represent polynomials if you have enough of them, univariate polynomials. But because of Weierstrass theorem, this says that I can approximate any continuous function. Because if we can represent a polynomial, we can approximate any continuous function. So that's a density result, and that's one part of what people knew in the 80s. This is for one variable, right? Okay, now we have to go from 1D to many Ds. And here, the observation is, it's really a statement. There is a proof in some footnotes of some papers, but it's something relatively simple to see, is that if you have an arbitrary multivariate polynomial, for instance, you can say, I want the multivariate polynomials, which is x1 times x2 times x3 times x4, for instance. And then see whether I can get it as the linear combination of univariate polynomials, where I have the freedom to choose the W. And you'll see that you have, in most cases, you have more terms, more freedom that you need to get this. You can do it. You have a lot of terms here that you can use. R is the dimension of the space of homogeneous polynomials of degree k in D variables. Homogeneous means with all the monomials have degree k. And this space is large, as we saw before. So you have a lot of terms there you can play with. You have a lot of parameters. You have, these are D-dimensional, and you have R of them that you can choose. So I'm not going to prove this, but there is a simple thing to, just to give you the intuition, is suppose you want to, you have a univariate nonlinearity, and so suppose I have just two variables, x and y, and now I have this univariate nonlinearity, and then of course through the trick that I showed before with the derivatives, I can get from x, I can certainly get x squared and x cubed and so on. And same for epsilon. I can get epsilon squared and so on. But how can I get the mixed terms, like x times y? For simplicity, let's assume that my nonlinearity now is a square. Then the square can get, I can get x plus y, and the square will give me the square, right? Now I want to use some other another units and then linear combination of it to get the x times y. And so this can be done by having x, y, here is plus, and then I have the nonlinearity square. And then I can subtract another units where I take x minus y, and I take the square, right? So now I have x squared plus y squared plus 2xy here, and here I have x squared minus 2xy minus y squared plus y squared. And when I take this, only the mixed term remains. So this is how you can by doing this kind of thing, you can get all the polynomials you want. So from univariate polynomials to multivariate polynomials. So okay, so that's part 2, and the third part is the one of going from multivariate polynomials to Sobolev spaces. And so here I define as this E is the minimum, the best error I can make by using let me see, x, one would be sorry for the confusion, but this is generic spaces. So suppose I have some b and x, and I want an element of x f, sorry, an element of b f being approximated by p in x. Okay, I define this term as the inf on the p, so the best I can do. And LP will be the norm, for instance, L2, the square. Then the theorem is if this is the space of our neural networks with one hidden layers and R units, and the space of function I want to approximate is Sobolev, dimension D, M smoothness. As I said, M could be 1, in which case essentially I don't assume anything about smoothness, just continuity. Then this is bounded by a constant, and this term R is the number of units to the M d minus 1. And this comes from the fact that I know a classical result that says that Sobolev functions d variables, and this is now the polynomials, also d variables. They can approximate with a bound of this type, where k is the degree of the polynomial and m is the smoothness of the function to be approximated. And so since I know that since R is in the order, as I calculated before, of kd minus 1, then k would be roughly R to 1 over d minus 1. And this means that EWM, I called NR, or this is the space of my neural networks with R hidden units. This will be essentially like WM PK LP, and this is C. Now replace the K here with R, and so I get R M D minus 1. So this one is a known. This one is known from theory of Sobolev functions. This I computed before in terms of the order, how many units I need, and then I just replace. Okay. So now, so one interesting thing is, as we said before, just 1 and 2 steps here imply that a shallow net represents arbitrarily well polynomials in PKD with R units, and R is in the order of k to the d. Okay. So this is the density through Weierstrass that people knew in the 80s, and this gives you a degree of approximation, how complex these networks have to be in order to do a good approximation. All right, so are we okay so far? So typically in approximation theory, most of the results are obtained using polynomials. A lot is known about polynomials, and this is no exception. We get these results about neural networks going through the polynomials. Okay, so the point here, in addition to the fact that you can approximate, but is also that there is a curse of dimensionality, as we said. The number of units you need increase exponentially with the dimensionality. So this is in general a problem both for shallow and deep networks, unless you make some assumption, additional assumption about the class of functions that you are considering. One assumption that I mentioned is to assume that the function you're trying to approximate are smooth. Then you can correct this by dividing by the smoothness. It's not clear, and if you're looking for a function that is the classification is giving you the label on ImageNet, it's not clear how smooth that function could or should be. It's often difficult to a priori make this assumption. Now, there is another one that we found a couple of years ago that seems potentially quite interesting, and this is what I would call for now locally hierarchical, maybe we can skip hierarchical compositional functions. Say in short, alt-C functions. So I can show that for this class of functions that I'm going to explain, deep networks of a certain type don't have the curse of dimensionality, whereas shallow networks do. Okay, so some example of this locally hierarchical, compositional function is a function like this. This is the simplest possible example. It's a function of 4 variables, but instead of being a generic function of 4 variables, is a function that has this graph. It's made up of 3 functions. Each one is a function of 2 variables. Right? So this function of 4 variables can be written as a function f1 of x1 and x2, another function f2 of x3, x4, and a function of both, right? So that's why it's composition of function, and each of the constituent functions, the functions in the compositions, has dimensionality 2 in this example. And you can see that I can, instead of having 4 inputs, I can have any power of 2, say 512, and build a binary tree like this, which will have log 512 layers. And it would be a function of many functions, but all the constituent functions would be functions of 2 variables. So we'll see that for functions of this type, the number of units you need don't depend exponentially on the dimensionality. They depend linearly on the dimensionality. Each of the functions has an exponential dependence on dimensionality, but the dimensionality is only 2. So we'll write this down. So this is an example of a function where you can avoid the curse of dimensionality. I'll show that if you have a network, a deep network, that has a similar deep structure. Another example, it's a little bit more complicated, but just to give you an idea of the function that also can be represented effectively with few units by a deep network, but not a shallow one, is this. I have just 2 variables, and I have, say, this is more or less arbitrary what I write here. Okay, and then I take something crazy, 2 to the 10. Now, this is a polynomial of very high degree, 2 to the 10. So if I want a shallow network, because of what we said before, I will need in the order of 2 to the 11 units. But if I represent this as a network which has multiple layers, then I just need 33 units. Because first layer will take care of this, and then I need 10 layers, each one of which takes the square, and these 10 layers, each one needs 3 units. Is that okay? Should I explain again? Now, this will be another example of a compositional function, something complicated, but you can write it as a function of one variable, the square root. This would be a function of 2 variables, and then you have another function of 2 variables. So it seems that most functions one deals with will be compositional. Difficult to think. If you can, actually, that's interesting, that can be a project or a problem set or homework. If you can come up with a non-trivial example of a function which is not compositional. I can tell you the example I came up with is the one of polynomials. Degree k in d variables. But otherwise, I find it difficult to come up with examples. Okay. So if you come up with something like this, let me know. You may get quite a number of brownie points. So the proof of this result is actually quite simple. Let's see if I so the theorem is that a deep network with suppose for simplicity, let's assume it has the same graph as the function, the compositional function we're trying to approximate. Then it needs, for each node of the function, it needs in the order of 2m units. This is the previous result we had because the dimensionality is 2m, considering the case of binary tree function. And then you have to find how many nodes in the function, which is d minus 1 for those binary trees. We have more general theorems for other types of direct acyclic graphs, but that's the simple binary case. And so you have this term which depends exponentially on the dimensionality, but then it's linear in the dimensionality. And interestingly, I'll come back to this later, most of the really successful neural networks, maybe the only one which are really successful, are convolutional networks. And convolutional networks have this structure. They have even more, but they have a locality, a local kernel, which is typically 3x3 in vision applications. Like in ResNet, on application to CIFAR or ImageNet. The basic kernel is not 2, it would be 9 variables. People have also used ResNets 2x2, where it would be 4 variables. And those are repeated in a convolutional network. So, and by the way, it's quite important that in the convolutional networks, you have not only this locality, oops. Yeah, this locality, but you also have weight sharing. Weight sharing means that H1 is equal to H2. Weight sharing means that we have even less parameters than the one I computed. However, weight sharing is not the magic that eliminates the exponential curves. The magic comes from the locality, from the fact that the constituent functions are local in the sense that they have a small number of inputs, a low dimensionality. Weight sharing improves that, but not in an exponential way. Okay, so let me prove quickly this. Let's see if I delete. Okay. So the proof goes like this. If I consider, again, this situation, it's easy then to recurse on this. So I have 3 functions, each one of 2 variables. I know that each can be approximated with, say, let's forget m, so it will be epsilon to the -2 units. And I also assume that H is Lipschitz with a Lipschitz constant L. So this means H of x minus a H of x plus epsilon would be at most. So this, I assume this, okay? And then I say I have that H H2 minus a I basically want to show that by this construction, if I have an approximation to a local approximation by h2 to a polynomial and to h1 to a polynomial, then since it's an approximation, there will be an error. The errors do not build up. So this kind of proof is essentially no error propagation as you go up. So I assume that h2 minus p2 is less than epsilon, and then I can write that h of h1, h2, and here I have, this would be the actual function, say that I want to approximate this. I want to know this is small, and in order to do this, I'll rewrite it just as, and then I add and subtract this, and then so far I have not done anything, but now I use, I guess it's called the Minkowski inequality. So I'll essentially say that this one norm plus the rest, so this would be less equal than h, this thing, h1, h2 minus h p1, p2, plus this part, this is h of p1, p2, pp1, p2, but this I know that that h, the arguments are the same. I know that h can approximate p within epsilon, so this term will give epsilon, and I know that this first term here, this first term will be also in the order of epsilon because of Lipschitz. Because P1 will be close to H1 and P2 will be close to H2. So the arguments will be close to each other. And so this whole thing will be in the order of epsilon. Is that okay? Should I do it again? So, as I said, the result, it's a pretty simple observation, but it's interesting because this may explain maybe one of the reasons why deep networks are better than shallow. Now, this assumes that you are using the deep networks with a hierarchical organization for problems in which the function to be learned or represented has this compositional structure. And that's not obvious. The intuition is, if you think about some of the problems, when you are trying to classify text or speech, which are a human artifact, intuitively it seems that they have a compositional structure in the sense that you don't need, in order to classify a sentence, to compute this letter with this letter here, but you can compute instead a syllable here, a word here, a word here and combine them. Same for speech. For images is a little bit different. They are not human artifacts, but again, does not seem when we classify this scene, this is a scene of a class, it does not seem like I need at high resolution a pixel there to interact with a pixel there, but I can compute, first objects and their parts maybe, and then combine them. So I don't know how to formally show you that images, classification of images correspond to functions that have a compositional structure. I don't know formally. If anybody has an idea, a lot of brownie points. But it seems intuitive, right? That you should be able to do it. Equally intuitive that not all problems can have this structure. For instance, I can imagine a number of problems in finance, in predicting the stock market, that don't necessarily have this structure. But there are a number of problems that have to do with images, text, and so on that are likely to have this kind of local hierarchical structure. And there are almost philosophical discussions one could have whether the compositional nature of these problems has to do with physical reality. A friend of mine, Max Tegmark, says, well, the Hamiltonian of physics are local, and then this induces objects that are clustered together and so on. Yeah, there is something, but I don't know. Or you can take the opposite argument. You say something like evolution, for some reason, developed deep networks in our brain. One reason may be connections are shorter than if you have to connect everything. Some stupid reason. And therefore, we have deep networks, and then deep networks can represent easily compositional function. And so these are the problems we understand and we care about. And the other ones, we don't. So in this case, the compositionality will essentially come from our brain, right? So anyway, these are fun discussions, a little bit too philosophical, but interesting to have. Let me finish here because we are almost Thanksgiving time, but there are a few other considerations, but we can do that in another class. I think I think the interesting message is that if you have problems that have this kind of hierarchical organization, I think many have, then deep networks, hierarchical architecture, have a good chance of doing much better than shallow ones. And the other point, which I think is quite interesting, is that you don't need weight sharing for this blessing of compositionality. Weight sharing helps, but is not the magic. The magic is really locality of computation. And I can speak another time about some thoughts about, from the point of view of basic theory of computation, you have elementary recursive function, if anyone knows about it, the fact essentially that you can choose a small number of primitive functions like multiplication and so on, and then build all functions out of it. I think in a similar way, if you now consider more of a distributed rather than sequential computation, you can start from function depending on the primitives you use, like for instance, sigmoids, RLUs. You can define functions that are simple in the sense they are just basically compositional, And then out of it, you can build all kinds of functions. For instance, by composing a lot of, by linear combination of a lot of compositional functions, you can get non-compositional functions. It's just that you get a lot of them. For example, polynomials are not compositional, but you can build them out of sparse polynomials, which may be. Okay. Have a good Thanksgiving.